Okay, so here we have three scenarios. One is uh, that the fastener is put into the member and then the nut is put in there, but there's no tightening. Okay, so it's just uh, in the rest configuration, nobody is carrying a load. Now what is done in the second figure is we apply some torque to preload the fastener. So what happens is as a result of applying that force Fi, this is also known as the preload, the length of the fastener increases. So you can see that this has increased. And then the length of the member has decreased. So there's a compressive force. Okay. So the deflections are going to be different. Okay. However, the load is going to be the same. So here I've sort of explained this. A is not yet tightened, B is when it's tightened. What happens is there are two different deflections. They can be easily computed if you know then the preload Fi and then the spring constant or the equivalent spring constant. So that's the second part. And then as I said, they are in series because they carry the same load. If they carry the same load, the two springs are in series. Okay, now what happens is the last part, the third part 3, is that there is some external load which is given by P. So this is actually the member in service where there's some load coming from some external means. Now remember that Fi is applied on the bolt to tighten it, and P is an external load coming on the members, not on the bolt. So when you do this, what happens is there is an extension of the, so when you apply this force, what's happening is this bolt is stretching by delta B, which means that the member is also going to be stretched by delta, capital delta, small delta M. So those two are going to basically take, they're going to have different deflections, but then they're going to have so they're going to have different forces, PB and PM. That load actually goes and it is shared between the two members. So if the deflections are delta B and delta M, we can find the relation between them by knowing the load PB and PM, such that PB plus PM, which is the load carried by the bolt and the member, is equal to P. P is the external load. So what we can do is, now that we have an expression, we know this from the stiffness. We are trying to solve for PB. So two equations, two unknowns, PB and PM. We can solve for PB. Okay, so that's what comes out. So I'm going to define a factor C, which is, as you can see, it is KB plus Km. It is a non-dimensionless number because it's springs constant divided by spring constant. And then if you want to find PM, load on the member, it's P minus PB, just comes from this expression. It is 1 minus C times P. So here is the summary. It is basically load on the member, load on the bolt, and then or the fastener, and then the C. Okay. So we'll need this expression later on when we try to do some calculations to figure out factor of safety. So this is basically the load sharing comes from C. Now, if there's an external pretension, which is Fi, and external P, it turns out that the net load on the bolt or the fastener is going to be plus Fi, because that load is basically in the same direction as PB, compressive. And then for Fm, the load is going to be negative of PM, so it's going to be minus Fi. So this is giving you the loads on the bolt and the member. Okay, so that's the total load if there is pretension. Again, there will be pretension. Obviously, if there's no pretension, Fi and is 0. In that case, Fb is Pb and Fm is Pm. Okay, so that's basically the loads. Now let's take this a little bit further and see how to relate the bolt load, which was what we discussed some time back, to the bolt torque, which is the new thing. Well, actually not new. We've already looked at torque. So if there's a preload Fi, and we have formulas for raising or lifting the load. This is just using the lifting the load, because most times we are interested in the more critical one is when do you lift a load? It's when you need to work against gravity or whatever the load is. So that's the more important formula. So here is the formula, which I basically took from the previous lecture on the torque. Okay, so it has the contribution due to the bolt, and then this is the contribution due to the collar. I've just explained this is just a recap of everything, bolt or screw. There's nothing new here. It's the same formula except that I replaced P with Fi. This was P in that. Okay, so that's the torque. This is the torque needed in order to tighten the bolt with a pretension Fi. So if you know how much torque you apply to pretension, you can figure out Fi or vice versa. So usually the torque is known. Basically, you have a measurement device which measures the force. Like for example, when you're tightening the screws on your tire, when you're say replacing the tires, there are gauges which tell you what the torque is. If you know the torque, you can find what that force Fi is. And that's actually something which is kind of important for tightening things like cars and aeroplane tires and so on. So here is the same formula, but substitution of 10 lambda equals L divided by dm. That's one of the angles associated with the screw. Okay, so that's not a big change. It's just going to get rid of two variables and replace them with one. Here is the final summary. Here I'm going to make some judicious choices based on what we observe. The collar diameter. So the collar is something which is sits on top of the member. It sort of helps to keep the forces in a given area as opposed to where it sort of protects the screw. Usually DC is 1.25 times D, where D is the major diameter of the screw or bolt. Then what we can do is we can substitute DC. It was part of this expression. It was the last part here, DC. So we just substitute DC with 1.25 D. And then what we can do is we can put things, sort of club things together and get this really simple expression, T equals K times FID, where K is a constant. And if you look at this constant, it actually is a function of only the dimensions, geometry. So the geometry shows up as dm, d, that's it. And then so dm, d, and lambda, so that's the geometry of the screw. And then the second is friction. So it's just a function of friction and geometry. So F, C, and F. Okay. So given a collar and given a screw, we sort of know F and FC based on manufacturing specifications. And of course, we know the geometry. So that constant K is supplied in a spec sheet. And then you only need to do this calculation with Fi and D, and that's how you get torque. So this is relating the initial tension needed to tighten the bolt. Okay, let's apply whatever we learned so far. Okay, so a fully threaded bolt with I'm just going to try to write down whatever I read in terms of variables, so I can use them in the equations. So the lead is 1 divided by 1/16 of an inch. The major diameter, which is always D with no subscript, is 0.75 inch. Is subjected to a load of 6 skip. So the load is P is 6 kip. The initial bolt tension is 25 kip. So initial tension is always Fi, it's 25 kip. The bolt and member stiffness, so we're given Kb is 6.5 m lbf per inch, and Km is 13.8 m lbf per inch. Okay, the area of the threaded portion is 80.373 inch square, which means that if you have, I'm just going to draw bolt. Okay, it's approximately, if this is dr, then this will be, it's actually not exactly equal to dr, but okay, it's basically this. Let me not put a dr there because then it will be misleading. So it's basically this area. So the inner diameter, this area is a t of the threaded part. Okay, there's an unthreaded part. And then d, capital D, now that I have this figure in place, is the outer diameter, always major diameter. Okay, an area of the minor diameter is 0.35. Okay, a 0.351 inch square. Okay, I think this is slightly wrong. This is probably not, this is the area of, this is actually AR. That's the minor diameter, DR, my bad. And then I think the AT is actually, there's uh, a spec sheet for that. It's not really something which is, um, you can calculate. It's somewhere which is AR. It's the area which you use to calculate the stresses. It's not comes to sorry, A, what did I say? A, R is this is 80, my bad. It's the area of the threaded part. It's basically a function of dr and p, and it's some nonlinear function. Okay, but that's something which is usually given to you. But AR is, that's right. And you can find, it says pi d square, pi dr square for sure. So this is dr, and you can find that. My bad. So AT is some area which is used for calculation purposes, comes from the manual or the spec sheet. Okay, I think I've covered everything. Let's start solving this. So compute the preload and service load stress in the bolt. Okay, so preload force is Fi. Service load force would be both Fi and P. Okay, so here is how to compute that. So I'll use the abbreviation, part A, preload stress. So I'll abbreviate this as sigma I because that corresponds to same as Fi. So sigma I would be what? Force divided by the threaded area. So Fi is given as 25. The threaded area, which is 80, is 0.37 given to you. So sigma I comes out to be 67.02 kpsi. Okay, next we need to find the service stress. Service stress, let's call that sigma B. So this will be all the, well, it will be the load on the bolt divided by the area of the thread. So FB was somewhere here. So FB is PB plus FI, which is CP plus FI. CP plus FI divided by AT. And in this expression, I think I know P, FI, AT, C is unknown. So this is an unknown. So let's compute that. The formula for C is KB divided by KB plus KM. So KB is 6.5, 6.5, KM is 13.8. So this is 0.32. Substitute that 0.32 P is 6, I think 6 kip. The initial pretension is 25. AT is 0.373. So sigma B equals 72.17 kpsi. So that's the stress on the fastener now due to the preload as well as service loads. That's the stress it will carry. So you can see it's not that high compared to the pretension, because the pretension was 25 while this was 6.5. Okay, so next we need to solve for torque needed to develop preload, assuming that the constant k is 0.2. So we need to compute the torque, and the formula is here, k times Fi times d. So it's the torque needed to develop the preload. This is the torque you'll use to start tightening the bolt before there's external load. So k Fi times d.